Topic 7.3, nuclear reactions. Nuclear reactions differ from chemical reactions in that nuclear reactions are processes that occur in the nucleus. When we talk about chemical reactions, those interactions occur between valence electrons of different elements. Nuclear reactions occur within the actual protons and neutrons inside the nucleus of a specific element. When we talk about nuclear reactions, the process that we're referring to is called transmutation. And we saw transmutation, or we talked about transmutation in the previous section when we looked at the different types of decay, alpha, beta, and gamma decay. These were types of what we call natural transmutations. A transmutation is simply the process of one element changing into another element. Remember what determines an element. It's the number of protons in the nucleus. And so when transmutation occurs, we're changing the number of protons in the nucleus of an atom through one means or another so that that atom now becomes a new element. And again, as we talked about before, when we talked about the different decay series, we have parent nuclei, and then we have our daughter nuclei. And the parent is what we start with, the daughter nuclei is what we finish up with. And so just a couple of examples, alpha and beta decay. You'll notice in each of these that we're starting with one particular element. In the alpha decay it's uranium, and it decays into thorium. And then in the beta decay we have thorium decaying into palladium. And we know that they're different elements. The uranium has an atomic number. The number of protons is 92. Thorium is 90. So we've gone from a nucleus with 92 protons to a nucleus with 90. And then the process of beta decay takes that thorium nucleus with 90 protons and changes into palladium, which has 91 protons. Those were examples of natural decay or natural transmutation. But we can also have what's called artificial or induced transmutation. And this is when we have two reactants. We have our parent nucleus, and then we also have some other nucleus that we're using, some high energy nucleus that's going to induce this artificial transmutation. When we're talking about the colliders and the Large Hadron Collider and a lot of the other super colliders that are around the world, this is what they do. They take nuclei, they get them going very, very fast, and they shoot them at other nuclei to try and get these types of artificial transmutation to occur. And so you have your stationary parent nuclei generally, and it's being shot with many of these other high energy nuclei to get this transmutation to occur, to get this nuclear reaction to occur. The first person to successfully artificially transmutate a nucleus was Ernest Rutherford. This was back in 1919. And Rutherford was conducting an experiment in which he was bombarding nitrogen gas with alpha particles. Remember, our alpha particles are those helium nuclei, 2 protons, 2 neutrons. And what he found was that there were fast-moving particles that were being generated that were traveling further than the alpha particles should have been able to. And so this told him that it wasn't alpha particles that he was looking at that were being produced. It must be something else. He also found that these new particles were actually being affected by a magnetic field, and based on that he was able to deduce that the particles being produced were protons. Now that nuclear reaction looks like this. We start with an atom of nitrogen, which has an atomic number of 7, so 7 protons, an atomic mass of 14, so 7 protons, 7 neutrons, and we shoot at it a nucleus of helium which has 2 protons. Now on the other side, what we end up with is an oxygen nucleus which has 8 protons, and then that other smaller particle that Rutherford detected was this hydrogen nucleus over here, which is simply a single proton. And it's important to note in this reaction that our conservation laws still hold. Over here we start out with 7 protons in the nitrogen, 2 protons in the helium, and so we have a total of 9 protons. Over here we have 8 protons in the oxygen, we have 1 proton in the hydrogen, so we have 9 protons here. And then 14 is our total mass, plus 4 is our total mass here, for a total mass of 18. And then 17 plus 1, we have a total mass of 18 over here. So mass has been conserved in this reaction. And in this particular case, you'll see that the number of protons and neutrons remains consistent from the left side to the right side. It's not always going to be the case, as in some of our decay series where we saw protons being converted to neutrons and vice versa, but the mass is always conserved. We have the same mass before and after. Another example of artificial transmutation actually being completed occurred in 1930 when Irene and Frederick Curie bombarded aluminum with alpha particles. And that looks like this. Here again we start with our aluminum nucleus, which has 13 protons, an atomic mass of 27. We're hitting it with our alpha particle, our helium nucleus, and again remember we'll sometimes see that as our little lowercase alpha. Same idea though. And you end up with a nucleus of phosphorus and a neutron. And so here you have something a little bit different going on, but still you have the mass being conserved. And so here, instead of a hydrogen being kicked off, or a proton essentially being kicked off, here you have a neutron being kicked off. But the nucleus holds on to both of those protons. So you go from a nucleus of 13 to a nucleus of 15. But again, mass before is 31, mass after is 31. And so this is a balanced nuclear reaction. Now in both of these cases, the particle that's doing the bombarding has been an alpha particle, but you should realize that it doesn't have to be. It can be a deuterium, it can be a tritium, it can be a number of the smaller elements, smaller nuclei that can be used to bombard other elements and induce these transmutations. The key to actually being able to figure out what's happening and what's going on and what the reactants and products are going to be is being able to balance these nuclear reactions. And to do that, we have to ensure that mass is conserved throughout. Okay, so let's look at a couple more equations and work through them just to make sure you have the right idea. So here we're starting with a nucleus of beryllium, 4 protons, atomic mass of 9. It's being bombarded with a proton, a hydrogen nucleus. We end up with a nucleus of lithium plus some unknown element. What does X represent? So let's look at our numbers. We have a mass of 9 here, we have a mass of 1 here, so we have a total mass of 10. Over here we have a mass of 6, so the mass number of X has to be 4. Here we have 4 protons, here we have 1 proton, 4 and 1, so we have a total of 5 protons. Here we have 3 protons, so in order to keep everything consistent, this has to be 2. And so our second nucleus that's produced here has an atomic number of 2 and an atomic mass of 4, which is going to make it an alpha particle or a helium nucleus. So we have 2 He 4. And so our balanced equation looks like this. And now let's do one more. Here we're starting with a nucleus of plutonium, which has an atomic number of 94. We're bombarding it again with an alpha particle, which has an atomic number of 2. We're getting as our products a neutron and some other new nucleus. And so again, we look at our atomic numbers and our atomic masses. our total number of protons is 96. Our total atomic mass is 243. And so our neutron is going to account for 0 protons but 1 atomic mass unit. And so everything else has to be in that nucleus X. And so that's going to give us a nucleus with 96 protons, and 242 is going to be the atomic mass. And that gives us a nucleus of curium.